We're going to calculate now the area moment of inertia I for this cross section, which has a centroid C over here at this location, which we found earlier. So we will now then calculate the moment of inertia about Z for part 1 and then for part 2 with our final goal of finding the moment of inertia of the whole part, but about Z at point C. So first, let's do each of these rectangles one by one. So we're going to do that. For part 1, the moment of inertia about Z1 at point C1 is 1 over 12 BH cubed, where the base is this length because the moment of inertia being calculated is about Z1. So we will do that, and what I'll get is 0.15 times 0.015 cubed divided by 12. That's what we got there. And then I'll also calculate the moment of inertia for part 2, which is also using the same formula, but now the base is this width, 0.015, and the height is the one that goes from here to here, which is 0.135. So 0.015 times 0.135 cubed gives me the moment of inertia that you see here, IZ2. So I have IZ1 calculated, IZ2 calculated. I also have, now that I know the moments of inertia, at this point about the Z2 axis, at this point about the Z1 axis for part 1 and part 2, what I want to do now is use the parallel axis theorem and find the moment of inertia of part 1, the contribution of part 1 to that moment of inertia about Z at point C, and then do the same thing with part 2 and use the parallel axis theorem to find the moment of inertia contribution of that part 2 at point C about Z. So starting with part 1, we then calculate the area, which we did earlier, A1, that's known. But then I can calculate then the distance from this point to this point, noting that the y-axis is downward, pointed downward as positive. So from this point to this point, that's positive, and I should be able to calculate that distance fairly easily. In this case, that's dy1. dy1 is calculated as 0.0355, and that's going to be squared. That's how you take this moment inertia of part 1 about Z1 and able to then use the parallel axis theorem by adding the area of that part times the distance between the centroid to the centroid of the part 1 squared. And by doing so, then you're able to get the moment inertia about Z. Then we'll repeat the process for part 2. And you can see here part 2 has an area, A2, that we were able to calculate earlier. And then we have this distance between this point and this point. But now that's going in negative y direction, that distance, that little distance there. And that little distance is going to be an amount 0.0395. So what we have there then is I can calculate the distance between this point and that point, but that's clearly in a negative direction. And that's going to be 0.0395 when you actually do the calculation. And that distance has to be squared and multiplied by the area of part 2, which I did earlier. And then you're able to then add all these numbers up to get the moment of inertia about the axis Z. It turns out that you can repeat the process about axis Y. And when you do that, you'll get the same moment of inertia for that as well. And I think it will be good exercise for you to try it. And you'll be very pleased that you get the same number. What about the product moment of inertia? For the product moment of inertia, that's very simple, because in this case, what you have is that the moment of inertia, the product moment of inertia for symmetric cross section like this one and like this one here is 0. So those two are 0, that's 0, and that's 0. The area for part 1 and part 2 are known, so that's completely known. And now all you have to do is, if you know the area A1 and A2, you just have to multiply area 1 and then determine the coordinates of part 1, determinants of the coordinates of the centroid, and simply find the distance in the y direction, but also the z direction. And so that'll give you this number and this number for part 1. I did it here for you for part 1. And then for part 2, you know the coordinates of this point, you know the coordinates of this point, so you can determine what is that distance there and what is this distance here. So that's this number and that number. I did it here for you, these two numbers. I know the area. So then I can then calculate the addition of all the numbers here to get, and there's a YZ there missing, you get the moment of inertia completely there. So actually, I was able to do that correction, YZ, moment of inertia YZ. I apologize for that. And now we're ready. That's how you calculate the moments of inertia. So we were able to find the centroid, the moment of inertia, and the product of inertia. So now that I know how to do that, I would like to then move to unsymmetric cross sections like I had promised. And yeah, so we will move to that next.